So, thank you.
That's me. So we are competing with types. It's very hard, huh, in Popl. Okay, so I will speak about abstract extensionality, where this idea comes from. If you go back to our studies and we go to what we call it standard model for computer science and programming languages, that's the model of computable functions. These are big, great guys. The equivalence is made by whether two programs compute the same function. Beautiful properties, compositionality, extensionality, referential transparency. All this is what we call the standard model. We borrowed that from physics, but I mean, we try to make true science here too, right? So that's our standard model. The problem, Simone Martini, who's working in lambda calculus, raises the following observation, that the standard model is to PL exactly the same as movement without friction is to mechanics. And this is very inspiring to us. A very nice quote from Simone. Basically, if you don't look at the equivalence as the function computed, but you look more in depth at what and how you compute, you discover complexity, which is intentional and not extensional, and many other properties. So functional equivalence is our standard model, but the reality works differently. So the question we try to answer in this paper is how much of the standard model holds in program analysis. Program analysis is concerning about the way you write code, and we will try to prove that formally. What is program analysis? Okay, so you have your program, you have a machine, Turing machine or whatever, that produce assertions automatically, hopefully automatically. And well, as usual, the only thing probably I know is abstract interpretation, and I'm still learning it. And we use abstract interpretation to specify the analyzer. So you have a concrete world of objects, which are properties of many shape, and you decide some shape, which is in that case the round, the circle, that will approximate the concrete world. And that's the abstract semantics. So the abstract semantics is the semantics computed in the abstract domain, while the concrete semantics is the semantics computed in the concrete domain. Okay, so we took a semantics for a programming language which is very simple. It allows to specify computable functions. You have the doing nothing, assignment, concatenation, if then else, while loop. And you have fixed point, of course, because of the while loop. This is the standard semantics. So where the friction comes from? The friction comes from when you do abstract semantics. Namely, instead of computing in the domain of concrete objects, you compute in the domain of properties. And you use properties you are computing in the previous step to generate the next one inductively. That's where the friction comes from. Okay, so but what kind of friction? The friction that comes from is exactly what we call, and the people that does the program analysis call false alarms. Imagine that you have the good states, and you know that the shape is the right one that you can approximate in your abstract domain, is a circle. And then you have the bad states outside. And you want to check whether the program computes something in the good state. Then that's true, that program computes inside S. A lot of people mistakenly confuse abstract interpretation with abstracting the interpretation, which is not the same. If I abstract that rectangle into my domain, I get that circle, which is abstracting the concrete semantics. If you are lucky, that corresponds exactly what you can compute by the abstract interpreter. And that means that the abstract interpreter exactly satisfies this equation, which we call completeness. You are complete. Everything you can prove in the abstract holds in the concrete, and vice versa, with respect to that domain. But often this doesn't happen, and sometimes the abstract domain get some approximation, and the approximation can be so bad that you can get outside your property. In that case, you produce a false alarm. And therefore, you are not able anymore to state that condition is true. Okay, so the point of this paper that comes from an older paper we made at Popl 2015 is that instead of having one program and looking for the analysis that better fits with that program, we fix the analysis and we look at all programs that fit with that analysis. Fitting means producing no false alarm. So we, in POPL 2015, we introduced a class of completeness class of programs. That's all programs for which the equation holds. So you have no false alarm. And of course, you have the class of all programs for which you may have a false alarm. These two class of programs is a partition. So you take the whole set of programs, okay, and you have a partition of them. The first thing that we can observe is that the class of complete programs is infinite. Of course, if you take the programs that do nothing, you don't lose precision, and you can pad that in a padding way and produce infinitely many programs the same way. Good. There is in that paper of 2015 another result that says that if this is all programs, then the class of complete ones covers all programs, contains all programs, if and only if the abstraction is straightforward. What does it mean? It means that whenever you are able to see something, but not everything, there is always a program for which you cannot be precise. This looks like a Rice theorem. So this is what we say. We try to look what of the standard model holds in this model with friction, which is program analysis. So whenever we can see something but not all, there always exists a program for which you cannot be precise. So what we did in this POPL 2020, we took this problem, this class of programs, so the analysis is fixed, and you look for the code that fits for the analysis, and we wonder, and we ask how the program equivalents behave when instead of looking at the function computed, you look at the analysis computed for the function. So the problem is program equivalence. Program equivalence is standard, is defined from the semantics computed by the two programs. And what we ask is what happened when instead of having the concrete semantics, we have the abstract interpreter here and here. Okay, it happens something interesting. The first thing is that take these two programs. These two programs compute the same function. You start from any integer, you produce 0 at the end. They look different, they are written in a different way, okay? But they produce the same function. So let's make interval analysis of them. So I run, of course, the second program runs faster. Then if you intersect with the exit condition, the first, you get the interval 0, 0, which is exactly the abstraction of the real computation. But here, the interval you get is bigger, is 0, 1. Why this? Because the interval gets larger and is a convex structure, so it includes elements that are spurious. They are not really computed, 1. So from the point of view of the abstract interpreter, these two programs are different, even if they compute the same function. This is the case of completeness. The other one is incompleteness. Okay, but incompleteness plays also another role. It can make different programs appear equivalent. Look at these. These two programs compute two different functions. One computes 1, the second computes 0. Then you run the interval analysis. You look at the end, intersect with the condition negated. You get that the spurious state makes appears here in 0 and here in 1 and makes the two output intervals the same. So the two programs that do not compute the same function, from the program analysis point of view, they are computing the same interval. So actually, the equivalence induced by an abstract interpreter is completely unrelated with respect to what a program computes. Good. This case is a case of that incompleteness produce equivalence. Okay, so we take all programs. Again, we split it in two classes. And then we introduce the notion of completeness clique. We borrowed this from Andrea Asperti intentional version of Rice theorem that appeared in POPL 2011 or something. I don't think it was in NIMS. So given a program P, that we fix, the completeness clique is the set of all programs that are equivalent with P, but for which you don't have false alarms. So you don't lose precision. And the incompleteness clique is a set of all programs equivalent with P from the concrete semantics, so they compute the same function, but you may have false alarms. Basically, these two sets intersect in this way. And we wonder what can we say about these sets. So you have the structure, then we try to look for the most obvious consequence. How many objects are inside there? Of course, you have infinitely many objects in both, because if you have a program that for which you don't have, if P, you don't have false alarms, then you can pad P with skip, and that's infinite. But if P belongs to the other set, so on the incompleteness set here, then those infinite sequences belong to that other one. So they are both infinite if one element is inside. This is obvious. Most interesting is the reduction. Can we make a reduction from one class to the other? So namely, can we remove, by acting on code, false alarms, or can we inject, by acting on code, false alarms? Okay, so you have all programs, and we try to see whether if we take a program for which you are incomplete, so it is in the incompleteness clique, we can transform it by an algorithm into one for which you are complete. No. It's enough two-point domain, or any ACC domain, any domain that has a finite chain only. This would correspond to proof termination. Why? Well, because if this transformation would exist, so if you can move from here to there, then we can make complete any abstract interpreter. But the abstract interpreter that runs on a finite chain domain converges in a finite number of steps. So imagine that you have here a program that runs all over this chain. It goes up and up infinitely many times, and the intersection with the guard is empty. Then what you get is that the abstraction of its concrete semantics is bottom if and only if you do not terminate. But if you are complete, you do the same check there in the abstract, but that is decidable. So you would decide termination for any programs, which is absurd. Okay, most interesting is about the completeness clique is the other way around. Namely, we can always inject imprecision. Okay, so you have this program. So now we move from complete into incomplete one. You assume that the abstraction is non-trivial. What does it mean? It means that, well, you want to abstract that semantic object, which is a shape, which is not in your abstract domain. Then the abstraction gets a bigger set. And in the bigger set, you have that because it's not the identity, there is a point here, and because it's not top. What does it mean being not top? Being not top means that you can see something about the computation. You don't simply forget about everything and say, I don't know. So that means that this shape has a point which is outside the circle. And what does it mean being not the identity? It means that this object, S, in the pentagon, is an object that does not contain the red bullet. Okay, so if you are in this condition, this is the condition of non-triviality of the abstract interpreter, then we ask this predicate, whether X, a point, belongs to S. S is the concrete object. So you can say this, you can say that X belongs to S in the concrete, but you cannot state that in the abstract, because the abstract is an over-approximation that contains the concrete strictly. So there are points that are not inside S concrete, but from the abstract interpreter, they are looked as being there. So around this predicate, you can build this code. This code do nothing except that basically in the concrete, it will execute like Q. In the abstract, you go through this double test, and you can activate any dead code. We will see an example here. Imagine that your state is 1, 3. Okay? And you have this program. Okay, look, if I make an approximation of 1, 3 in the intervals, I get 2 in the middle. 2 is not computed. It's not something, it's an approximation. It's a spurious state that appears out. Okay, now I can generate that piece of code by injecting a function, an assignment x to -10, that basically will never be executed. It's a totally dead code. But it is only executed if at the entrance I get with the interval 1, 3. And this is because the approximation includes an object too, which is not in the semantics. So at the end, instead of 0, I compute minus 10, 0. So it seems that I can always inject imprecision into my abstract interpreter by hacking the code and keep the semantics equivalence, the concrete semantics equivalent. What we proved out of these observations and lemma is that an abstract property, if I take Rice's theorem, I say what is an extensional property? An abstract property is something that is closed by the abstract semantics. Is extensional in the sense of Rice if and only if the abstraction is trivial. So basically, there is no way to escape from this problem. We also studied the transformations about the data flow, but I skipped this because there is not much time. It was nice colors. Okay. Okay, so conclusions. The first thing that we can say is that any non-trivial abstract interpretation reveals is intentional. So reveals intentional aspect of the code. Namely, it reveals how the code is written together with properties of what you compute. All the nice things, the compositionality, I missed the slide, but you can find it in the paper. Extensionality, we have seen the theorem. Referential transparency depends on the extensionality. All these nice features do not hold unless you are trivial. So each time you get into the real world of program analysis, friction makes you, destroys all the nice, beautiful results from computability. A nice problem is the following. If I take this partition and I ask whether the class of programs for which you are precise is Turing complete, the answer is no. No, why? Because if it's Turing complete, I can build an interpreter there, and I can build a specializer there. I take first Futamura's projection, and I can compile an object from the click of P into the incompleteness click of P, which is absurd, we just proved. Interestingly, the other side of the moon is Turing complete. So you can always build an interpreter in the side of incomplete programs for which you are imprecise, and a specializer, and work there. So basically, this opens the following question. If we look prospectively, program analysis is like complexity. It's a complexity measure. Complexity is intentional. Program analysis is intentional. The question that comes out from this is whether we can have an implicit theory of program analysis. Namely, by checking the code, I can tell you how much false alarms you will produce. The second stuff is that we would like really, and now we are working on, is instead of refining the abstract domain, I worked on abstraction refinement since ever, and this year is 20 years that my completeness paper in Journal of ACM. So it's a long-standing work that I do with my group. But instead of refining the abstract domain, why not changing the code to cope with the abstract interpreter? So instead of having a super skilled engineer that generates a new abstract domain and a new abstract interpreter, I hack the code to make better, to behave better. That corresponds to ask whether the completeness class belongs to the Chomsky hierarchy. Where? Of course, it doesn't belong to type 0. We just proved it in this paper. It probably fits inside some class, and that's the question that we would like to approach for the next years. Thanks.
Thanks a lot, Roberto. So we have some time for questions.
So clear? Yeah. Oh.
Hi. Can you elaborate on what you mean by an implicit program analysis? How is it not implicit currently?
implicit, somehow I would like to have a kind of type theory that check my code and detects where a given abstraction and a given abstract domain, and therefore an abstract interpreter, will fail to produce a precise result. Similar like in implicit complexity, where you type check a code and you say it's polynomial, or is log space, or whatever. I would like to have this. We have a first on this in the POPL 15, but still.
Okay, so I have one regarding to your second to last slide, where you propose to reflect on the way to code to get a better analysis result instead of just refining the domain. Could you elaborate a little bit on that? In particular, did this work inspire, of course, necessarily partial, but possibly systematic ways to improve the situation a bit, even if we know that we are not going to make the analysis
we cannot make a compiler from one to the other. But the idea is that if your code is sufficiently well structured, and you can even just hack basic blocks, because the problem in making complete is guards. So if then else, while loops are all guarded commands, and these guards are generate always incompleteness. So, but if you can constrain the incompleteness to some specific part of your code, then your analysis will cope better. This, of course, is a long-term project about this. So it's not. We have just preliminary results. And
okay, we have only very little time. Sorry.
So, you also lose completeness in abstract interpretation from widening.
Oh, yeah.
Your definition here is
if you have widening, you're immediately incomplete, because you are complete with widening when the widening is the least upper bound. So by adding widening inside the domain, you immediately lose precision. No way. And of course, all these results becomes easier and easier to prove. The difficulty was to prove for the case where you don't have widening, where you are the most precise abstractions. Okay.
Thank you, Roberto.
Thank you.